One of the most useful problem-solving techniques is to take your problem and break it down into more manageable pieces. For example, we can differentiate sums and differences of functions just by adding or subtracting the individual derivatives. But what if we have two functions that are multiplied or divided? What do we do then? Every weekend I get pizza with my parents. We're originally from New York, so it's kind of a required thing. We talk about life, how things are going, occasionally the state of the world, and at some point I often end up telling them about whatever math I happen to be teaching or learning about in my classes. And every time, my dad just kind of looks at me, smiles, and says, addition, subtraction, multiplication, and division. That's all the math I've ever needed. Now, I don't think that's really true. There's a lot more to math than arithmetic, and I'd argue that there's a lot of math that many people, including my dad, intuitively know. They just don't think of it as math. But in another sense, I think he's got a point. When it really comes down to it, a lot of math really just boils down to finding more sophisticated ways of doing these four things. Here's an example. Suppose a tech company comes out with a brand new gadget. Each month, they gradually lower the price, and as a result, more people want to buy it. The quantity demanded goes up. If we multiply these two things, the price per unit times the number of units demanded, then we get the revenue that company makes off that gadget in any given month. So if we assume this model, how's the company doing 5 months after the gadget's introduced? Is its revenue increasing or decreasing? We've once again found ourselves in a new situation. We need the derivative of a product of two functions. What do? Well, we might start by thinking of the patterns we've seen thus far. We already know that when we add or subtract two functions, and then take the derivative, that's the same as just adding or subtracting the individual derivatives. We called those the sum and difference rules. Well, does that maybe work for multiplication too? Is the derivative of a product just the product of the individual derivatives? Well, let's think about that for a moment. What would the units of each of these derivatives be? dr over dt would be measured in dollars per month. dp over dt would be dollars per unit per month. And dq over dt would be units per month. But then if we multiply dp over dt and dq over dt, those per months combine together, and we get a unit of dollars per month squared? That's not right. So that tells us we can't just multiply the individual derivatives. Would have been nice, but our answer wouldn't have made logical sense in any real-world context. So there has to be something else we can do. Let's take a different perspective for a moment. I find a lot of things much easier to understand in math if I can visualize them. And actually, I'd wager you're probably the same way too. Now, there's a good chance you've heard people talk about these so-called learning styles. Some people say they're visual learners, others are auditory learners or kinesthetic learners, that kind of thing. What a lot of people don't realize is that actually that's been shown to be false. Instead, what researchers have found is that everyone benefits from learning in multiple ways. We're all visual learners and auditory learners and kinesthetic learners and so on. So in that vein, it always helps to have a picture. And my favorite intuitive picture of multiplication is the area of a rectangle. In this picture, we've got the length and width of a rectangle being controlled by two quantities f and g, in which case the area is f times g. Now, suppose we nudge those two dimensions by a tiny bit. F changes by a small amount, df, remember we called that a differential, and g changes by a small amount, dg. How much does the area f times g change by? We can split up that new area into different pieces. One chunk of the area is the tiny change df times the entirety of g. And another chunk is the entirety of f times the tiny change dg. We also get this piece here, df times dg. But if df is really tiny, and dg is really tiny, then df times dg is really, really tiny. So tiny, in fact, that we can essentially just throw it out. Technically, there's a more complicated reason for why we're allowed to do this. It has to do with limits, which we'll learn about later, but that's the basic idea. The only pieces we need to worry about right now are df times g and f times dg. Now, if f and g are functions of some variable x, then they'll change when x changes. So if we divide both sides through by dx, we end up getting a formula for the derivative of f times g in terms of f and g and their derivatives. What we've now developed is the product rule. If we want to differentiate a product of two functions, we look at all products we can make when we do one derivative at a time, and then we add all of those products together. So the derivative of f times g is f prime times g plus f times g prime. And the units work as well. If we let h stand for f times g, then the units of h are the units of f times the units of g. Remember, that's how multiplications of units and dimensions work. And if you look at the units of the derivative, since each term only differentiates one function at a time, we only end up with units for x once in the denominator rather than twice. So we get the units of f times g per the units of x, just like we'd expect. Let's go back to our tech company and see how we can use this new rule. We have dp over dt, which is negative 20, times the entirety of the function q. Then plus the entirety of p times dq over dt, which is 200. We could clean this up by multiplying everything out, but that's only if we really need to. That's our choice. So if we plug in t equals 5, then we get 2,000. So now we know that 5 months after the gadget comes out, the company's revenue is increasing at a rate of $2,000 per month. There we go. Now, there's one possible objection you might have thought of here. P and Q are just linear functions, which are kinds of polynomials. So why didn't we just multiply out r of t first, and then take the derivative using the power rule? Wouldn't that have been easier? Well, maybe, yeah. And you can check that if you did it this way, you should get the same thing as what we got when we used the product rule. But that doesn't always work. What if we had something like this, an exponential function times a trig function? That's the kind of model that shows up when, say, you have a damped spring, like a bungee jumper that jumps, bounces up and down, but eventually levels off. There's no way we can turn this kind of function into just a polynomial, so if we want to find the derivative, say to find out how fast the bungee jumper is rising or falling, we have no choice but to use the product rule. And there's a philosophical reason too. Forcing ourselves to keep the pieces separate lets us see how each one contributes to the derivative, so that we can apply what we find to any situation. And by the way, that includes taking a new look at old situations. You could use the product rule to actually figure out the derivative of x squared, x times x, and maybe even extend what you find to see why the power rule works in the first place. With multiplication taken care of, the next natural question is, what about division? If we have one function divided by another, how could we find the derivative of that quotient? Well, this is a good time to mention another useful tip for problem solving in math. If you're faced with an unfamiliar problem, try turning it into something you are familiar with. And this problem in particular brings together a lot of things we've seen so far. First of all, remember that division is really just multiplication under the hood, multiplication by the reciprocal. For example, 10 divided by 2 is really equivalent to saying 10 times 1/2. So we can rewrite f divided by g as f times the reciprocal of g, that is g raised to the negative 1 power. Now, since we rewrote our quotient as a product, when we take its derivative, we can just use the product rule. We've got the derivative of f times g to the negative 1 plus f itself times the derivative of the quantity g to the negative 1. That last part requires a bit more care. First of all, we need to use the power rule. Since we have stuff raised to the negative 1 power, so we have negative 1 times g of x to the negative 2 power. But since the stuff inside that negative 1 power is itself a function, g of x, we also need to use the chain rule and multiply by the derivative of g. Take a moment and pause here if you need to make sure you understand where each part of this comes from. We've used the product rule, and the power rule and chain rule each came in as part of the calculation. Make sure you see how everything fits together before you keep going. Okay, let's clean this up a bit. We can turn those negative powers back into fractions, and then to combine those two fractions, we can multiply the top and bottom of the first one by g of x. So they have a common denominator of g squared, and thus we can add them up. And there we go. What we now have is known as the quotient rule, a way to find the derivative when one function is divided by another. Notice that the top looks a lot like the product rule, but now there's a minus sign, and we also have g squared in the denominator. Now, to be fair, this rule looks a little more complicated than some of the other ones we've seen thus far. How can you remember which part goes where? Well, one thing you could do is learn a mnemonic. Personally, I learned the quotient rule as a rhyme. Low-de high minus high-de low. Square the bottom and off you go. The high and low are the parts of a fraction, the numerator and the denominator, respectively, and the d stands for derivative. And actually, when I do this in practice, I say this rhyme out loud every single time, seriously. But we can also do better than just relying on a mnemonic. We can also make sense of each part conceptually. Think of it this way. If we increase the numerator of a fraction, then the whole fraction increases in size. So the f prime times g term is positive. But if we increase the denominator, the fraction itself decreases. So the f times g prime term is negative. And then dividing by g squared does two things. First of all, it reminds us of the chain rule that got us here in the first place. We had to take the derivative of g to the negative 1, so that gave us a factor of g to the negative 2, and that also explains the minus sign. But it also makes sure that the units work out to the units of f over g per the units of x. If you want, you could verify this on your own, or I've done it here and you can work through it and see where everything comes from. Okay, let's do an example to really nail down how the quotient rule works. Imagine a small town supplies recycling bins to 15% of their population, but they want to start raising that number. Gradually, of course, because you know how slow things are in the government. Suppose the cost, C, of doing so is 25,000p divided by the quantity 100 minus p, where p is what percent of the population they're supplying with recycling bins. Let's go ahead and find the derivative using the quotient rule. We've got low, 100 minus p, times d high, the derivative of 25,000p, which is 25,000, minus high, 25,000p, times d low, the derivative of 100 minus p, which is negative 1. Square the bottom, so 100 minus p all squared, and off we go. There's the derivative. If we clean things up a bit by multiplying out the numerator, it actually simplifies even more, and we end up with 2.5 million divided by the quantity 100 minus p squared. Remember that the town is currently supplying recycling bins to 15% of their citizens. So if we plug in 15 for p, we end up getting about 346. And the unit is dollars per percent. So if we think of this in terms of sensitivity, then if the town were to supply recycling bins to an additional 1% of the population, it would cost the town an additional $346 and some change. And that's a statement in plain English that you can bring to the city council, and they should hopefully be able to understand it. Whether they act or not, well, that's a different story. Calculus can't solve that problem. Anyway, the product rule and quotient rule are the last missing pieces of the puzzle that let you take derivatives of just about any function you can get your hands on. Do keep in mind, though, that some problems have multiple ways they can be solved. So don't be afraid to kind of massage your function algebraically a little bit if you think one way might be easier than another. After all, like we said before, being able to choose the most efficient or elegant way to solve a problem is one of those things that makes a good mathematician.